Let's talk about building better code. Making that jump from writing code that just works to crafting software that's clean, easy to maintain, and actually built to last. We're going to dive into the tools and the mindset that get you there.
Oh, you have. We've all been there, right? You get a feature working, and then you just slowly back away from the keyboard, hoping no one ever asks you to change it. Because deep down, one little tweak could bring the whole house of cards down. So why does that happen?
Well, it's because software is never really done. It's a living thing. The client wants a new feature, a new technology comes out, the business pivots, something is always changing. So the real challenge isn't just solving the problem today, it's building a solution that can adapt to whatever tomorrow throws at it.
So how do we handle all that constant change and complexity? We start with the fundamentals, our basic toolkit, Object-Oriented Programming, or OOP. It's a way of thinking about code that's built around a few key ideas, designed specifically to help us build more flexible and robust software.
At the heart of OOP, you've got what we call the 4 pillars: abstraction, encapsulation, inheritance, and polymorphism. Now, these aren't just fancy buzzwords to throw around. They are genuinely powerful concepts that help us write smarter, more resilient code. So let's break them down one by one.
First up, we have abstraction. And really, this is all about simplification. It's about looking at a complex, real-world thing and asking, what's the only stuff I actually care about for this specific problem? You focus on the essentials and just ignore the rest. It keeps your code from getting totally bogged down in details that don't matter.
And this example just nails it. If you're building a flight simulator, your airplane object needs to know all about speed, altitude, fuel levels, all that complex stuff. But for a flight booking app, all it needs to know about is the seating chart and maybe the flight number. It's the same airplane, but 2 completely different, simplified models. That's abstraction in a nutshell.
Okay, next up is encapsulation. You can think of this like the hood of a car. You don't need to be a mechanic to drive it, right? You just use the steering wheel, the pedals, the gear shift, a really simple interface. All the greasy, complicated engine stuff is hidden away. Encapsulation does the same for our code. It bundles the data and the methods that work on that data together and hides the messy internals. It's a fantastic safety feature.
And here's where it gets really powerful. The airport class here doesn't care if it's talking to an airplane, a helicopter, or even a mythical griffin. As long as that object promises to behave like a flying transport, it can land, it can take off, the airport knows exactly how to work with it. The messy details of how each one flies are encapsulated inside the object itself.
Our third pillar is inheritance. This one is probably the most straightforward way to reuse code. It lets you create a new class that's a more specific version of an existing class. The new child class automatically gets all the features of the parent, so you don't have to write all that code from scratch. You just add the new specialized stuff you need. And this classic example makes it super clear, right? A cat and a dog are both types of animals, so they can both inherit general animal things, like having a name or the ability to eat and sleep. But then the cat class adds its own special behavior, meow, and the dog class adds bark. You get to reuse the common code and specialize the rest.
And that brings us to our fourth and final pillar, polymorphism. It literally means many forms, and this is where your code starts to feel like it has a mind of its own. It's the ability to treat different objects in the same way, but have them respond with their own unique behavior. So check this out. Let's say you have a bunch of different animals, but you're just treating them all as generic animal objects. When you tell each one to make sound, polymorphism is the magic that makes sure the cat object actually meows and the dog object actually barks. Your main program doesn't have to know or care what kind of animal it is. The object itself knows what to do. It's incredibly powerful.
Okay, so we've got our tools, the 4 pillars of OOP.
But just having a hammer and a saw doesn't make you a carpenter, right? You need a strategy. You need to know how to use those tools effectively. And that's where a couple of golden rules of design come in.
This is rule number 1, and it is a big one. Sometimes you'll hear it called encapsulate what varies. The core idea is simple. Find the parts of your code that you know are going to change and wall them off from the parts that are stable. That way, when a change inevitably comes, you're just swapping out one small component, not performing surgery on the whole system.
Just look at this before and after. On the left, the tax calculation logic is buried right inside the order class. We know tax rules change all the time. That's a ticking time bomb. On the right, we've pulled that logic out into its own dedicated tax calculator class.
Now the order class is simple and stable, and when the tax code changes, we only have to touch that one isolated file. So much better.
And here's the second golden rule, which is an absolute game changer for writing flexible code. It sounds a little academic, but what it really means is this. Your code should depend on abstract concepts, or contracts, what we call interfaces, not on specific, concrete details. This makes your code way less brittle and way more adaptable.
This is just a perfect way to visualize it. If you build a cat that can only eat a sausage object, well, that cat's stuck. But if you design your cat to eat anything that behaves like food, anything that fulfills the food interface, then you can introduce fish or kibble or whatever later on, and you never have to change a single line of code in the cat class. It's that flexibility that we're after.
So we have our OOP tools, and we have our guiding principles. The last piece of this puzzle is taking those ideas and using them to build proven, repeatable solutions to common problems. And that, my friends, is what we call design patterns.
So what is a design pattern really? The most important thing to know is that it's not a piece of code you can just copy and paste. Think of it more like a blueprint from a master architect. It's a battle-tested, proven strategy for solving a specific kind of problem that pops up over and over again in software design.
And this comparison here really helps clear things up. An algorithm is like a recipe, a specific step-by-step set of instructions to get something done. A design pattern is like a blueprint. It shows you the structure, the components, and how they all fit together. But you, the engineer, still have to build it using the right materials for your specific project.
And these patterns tend to fall into three big buckets. You've got creational patterns, which are all about how to create objects without making your code dependent on specific classes. Then you have structural patterns, which help you compose objects and classes into larger, more flexible structures. And finally, behavioral patterns, which are all about how objects communicate with each other effectively.
Okay, let's bring this all home, because none of these ideas, OOP pillars, design principles, design patterns, exist in a vacuum. They're all connected. They're all part of a larger mindset, a way of thinking about building software that's designed for the long haul.
And this right here is the big picture, all the ways we connect our objects, from a simple weak dependency all the way up to strong relationships like composition or inheritance. It's all part of the same story. It's all about managing relationships and dependencies built on that foundation of OOP and guided by those core principles we talked about. It all fits together.
So, I'll leave you with this final thought. If you think of writing code as a form of architecture, you really have a choice to make every time you start a project. You can just start laying bricks, writing individual lines of code and hoping it all holds together. Or you can start with a blueprint, using these proven principles and patterns to design something elegant, strong, and truly built to last. The choice is yours.